A lot of people have asked me about getting started with computational neuroscience. In this video, I will share with you my experience and talk about some common misconceptions about this absolutely exciting field. Here is the rough outline for you to navigate around, but watching the entire video from start to finish will definitely be worth it. Anyway, without further ado, let's dive straight into it. My name's Artem. I'm currently finishing my bachelor's in biophysics and computational neuroscience at Moscow State University. On this channel, we talk about the brain and do deep explorations of interesting neuroscience concepts and papers. If you're interested, consider subscribing not to miss anything. First of all, let's talk about what computational neuroscience even is. It's still a very young field, which basically refers to using computers to understand the brain. And this using computers part can be very loosely divided into two groups: data analysis and simulations. Be warned though that it's not an official distinction by any means. It's just the way I personally like to think about this stuff, and I think it could be conceptually useful. First of all, there is an overwhelming amount of data we collect through experimental techniques by observing the real brain. And a big part of computational neuroscience is dealing with these insane amounts of information. To give you a concrete example, suppose you have a video recording of calcium dynamics unfolding in an astrocyte. This is a type of a glial cell in the brain. It's quickly becoming a hot topic because these calcium signals are very likely to contribute to information processing carried out by the brain. We just don't know exactly how. Anyway, before you can do something useful with this data, it surely needs pre-processing, like denoising, filtering, selecting good clips. Then, depending on the design of the experiment and the hypothesis you're testing, you want to extract some useful information from this data. And that involves writing code to quantitatively describe these calcium events and somehow link them to animal behavior or physiological state. Finally, you usually want to perform some statistical tests to check the significance of your results, create plots and other visualizations. This is a simplified example, but it nicely illustrates the backbone of a typical workflow. And we, as computational neuroscientists, carry out every stage of this analysis. But it is also very useful to generate artificial pieces of data by running what's known as in silico experiment. When we want to understand how something works, oftentimes we want to build a simplified model of this phenomenon as an attempt to explain it. Detailed numerical simulations can help us understand the mechanisms behind brain functions and test various hypotheses. Results from these simulations can be then compared to experimental data to assess how well your model describes reality. To expand on our example, suppose you want to understand how the morphology of the cell, and that means like its shape and different branching patterns, how it affects the dynamics of intracellular calcium levels. In that case, and it's actually something that I'm currently doing as part of one research grant, it's helpful to build a simplified model of an astrocyte by setting up a system of differential equations and writing code to run this simulation and find numerical solutions. Then, by twisting and turning the cell's geometry in obscure ways, you can actually get an insight into how the shape affects the calcium levels. Poking the model at different angles and probing it in such a way can lead to the discovery of some emergent phenomenon that would otherwise remain unknown. Well, I hope that wasn't too discouraging. I've given an example with astrocytes mostly because this is what I have been working on recently, but computational neuroscience is definitely not limited to that. You can work on a variety of topics, such as EEG, fMRI, neuron electrical activity, ion channel biophysics, brain connectivity, and many more. With that in mind, let's talk about necessary skills, which you will continuously sharpen if you decide to embark on this exciting journey. The most important one is, of course, coding. And this will become your bread and butter no matter what topic or project you're working on. I mean, unless you're one of those mathematical and theoretical neuroscientists, but that's a very rare breed. Next one is the knowledge of neuroscience itself. It's impossible to conduct any meaningful research when you don't know the nature of the object you're studying. It involves things like how cells work, how action potentials are generated, and how cerebral cortex is organized. And finally, necessary mathematical toolbox, both underlying the algorithms and serving as a language to describe certain biological phenomena. Keep in mind that this list is not exhaustive, because neuroscience is a very interdisciplinary field. Depending on the topic, at some point you might find yourself reading up on chemistry, quantum physics, or even economics. It will become clear when you dive deeper into doing real research projects. And now let's discuss each component in more detail, starting with coding. One of the most popular questions for a lot of people is what programming language to go with. From my experience, the two most popular choices are Python and MATLAB. There is also a programming language called Julia, under active development and aimed at scientific computing. It's very promising, but still quite young and not as widespread as Python, for example. Now, when you join a lab as a PhD student or an undergraduate, it is very likely to already have some inner culture established. Things like custom-written modules and data processing workflow. In this case, it's better to fit in and use what they are using, at least in the beginning. For self-studying though, when you are on your own, you can choose whichever one you want. Personally, I went with Python because it's free, while MATLAB is a proprietary software, which could be costly to obtain if you're not affiliated with the university. Additionally, nowadays Python is more popular, and there is a ton of packages for doing almost everything, while MATLAB is kind of a dinosaur at this point, which is slowly going away. But honestly, the choice of language is way less important than you might think. This is a common mistake people make, and it directly affects the way they practice. You see, what really matters is the skill of constructing algorithms, not the exact language you're using to do so. Because if you have a lot of experience with MATLAB or C++, for example, then switching to Python will only take a couple of weeks, because the only thing that's different is the syntax, and maybe some libraries you're used to. But all the algorithms, all the fundamental concepts, such as conditionals, loops, functions, variables, are exactly the same. When people get into programming for the first time, they usually limit their learning to either simple theory or plain syntax practice. For example, what dictionaries are and how to use them. This is a great starting point for sure, but by no means should it be the final stop. You may have learned the syntax, but you haven't learned coding per se, because no one can fully learn it. It's something that you continuously master. That's why after you learn the basics, the absolute best way to advance as a programmer is to make emphasis on solving problems that are not straightforward, but involve some algorithmic thinking, not plain syntax practice. Because in the actual research, you will have to find creative solutions to non-standard problems that arise. For example, converging between two different representations of your datasets. And not everything will be spoon-fed to you on Stack Overflow. It will be tough when you don't have the skill of applying the knowledge and cooking up algorithms of your own. So, how do you practice algorithmic thinking? Personally, I come from a background on computer science, and particularly competitive programming, which I used to do during middle and high school. And I believe that has given me a huge advantage as a neuroscience researcher. Solving tricky problems while trying to find a way to parameterize recorded brain signal was just like participating in an informatics Olympiad once again, only way more exciting. Different programming Olympiads are amazing sources of such non-straightforward exercises for you to practice with. You can find them on different websites such as codeforces.com. Codeforces contains a huge set of practice problems from previous competitions of various levels, and there is an inbuilt testing system so that you can paste your code right into the browser, choose a language, and the system will run tests and give you the verdict whether your solution was correct. I know it can seem scary, but trust me, it will pay back. It helps to internalize different algorithms in your head, and you learn how to adapt them to new problems. No getting started type of video would be complete without a set of recommended textbooks, providing you necessary background knowledge. To get you started with the field of neuroscience, there is quite a number of really great textbooks. From the ones I'm personally familiar with, I can recommend Neuroscience Exploring the Brain by Baron Connors, if you prefer a lighter version. In case you are opting for something more hardcore or have some previous experience, there is Principles of Neural Science by Eric Kandel. This is a very thorough read with a lot of interesting details, which is considered to be the Bible of neuroscience by a lot of people. From the realm of more popular sources, I can't recommend enough a fascinating book by Yuri Buzhaky titled The Brain from Inside Out. This is a wonderful read which contains some paradigm-shifting ideas about how we should approach studying the brain. Also, keep in mind that the most recent information can be found in research papers. I highly advise you to get into the habit of regularly reading research papers. It can be very daunting at first, but over time, you will get significantly better at it. I have a video about discovering interesting research papers right here, and also the one about reading them effectively. If you would like a taste of a more computational side of things, there is a great classics by Diane and Abbott titled Theoretical Neuroscience, Computational and Mathematical Modeling of Neural Systems. In case you're interested in the models of neurons and excitability, I highly recommend a fascinating textbook by Eugene Izhikevich, Dynamical Systems in Neuroscience. It really helps to build intuitive understanding behind concepts in dynamical systems theory, such as phase portraits and bifurcations, in the context of neurons. I personally used it very often as a supplementary material in preparation for mathematical modeling classes. Finally, check out a free online textbook, Neuronal Dynamics, written by researchers from EPFL. The big advantage is that it also contains Python exercises to practice with. And while we are on the subject of books, I'd like to thank the sponsor of today's video. Shortform is a platform to supercharge your reading. They offer book guides, very detailed summaries of books, which also contain interactive exercises and references to related information sources. This really promotes interlinking of ideas and helps to see the big picture of the topic. I find Shortform very useful when searching for new books and extracting key ideas, thus guiding the reading process. Shortform releases new book guides every week, and they cover a great deal of genres, from science and education to self-improvement and productivity. If you're interested, use a link down in the description to get 5 days of unlimited access and 20% discount on annual membership. Now, situation with math is a bit tricky. On one hand, it is an essential tool and, after all, the language of science. And sure, there are certain topics that are absolutely invaluable no matter what you do. For example, fundamentals of linear algebra, which underlie all numerical computing and data manipulations. In case you would like to brush up on that, there is a great online course on MIT OCW by Gilbert Strang, containing video lectures and textbook exercises. And the playlist by 3Blue1Brown, The Essence of Linear Algebra, is a must-watch, at least once. But at the same time, learning math can be a pitfall. It happened to me during my freshman year of college. I had the false impression that I have to first learn all the math perfectly before I can actually move forward and do some meaningful computational neuroscience. And so I would just bury myself in textbooks on real analysis, complex variables, and even some proof-based linear algebra. And the process was very slow and not really enjoyable because I was learning it for its own sake, like some sort of prerequisite, with no interesting problem at hand to apply the knowledge. But what I then realized, and looking back, I really wish I knew it sooner, that I don't really need most of this stuff, because you can't learn everything in advance. Instead, it's a much better approach to just dive straight into doing exciting computational neuroscience. And when you encounter situations when you realize you don't have a necessary mathematical prerequisite, use online resources to learn that piece of math right on the spot, in parallel to applying the knowledge towards solving real problems. Additionally, the exact mathematical toolbox will be determined by the type of project you're working on. For instance, if you're interested in connectivity and network neuroscience, then knowledge of graph theory is essential. Meanwhile, if you're drawn to building realistic models of neurons, you'll probably want to make more emphasis on dynamical systems and mathematical physics. But again, don't try to read the graph theory textbook cover to cover before doing network neuroscience. Begin by playing around with projects first, and let that process guide you into which aspects of graph theory to make emphasis on and what to leave behind. I've mentioned several times at this point how important it is to do projects. But what the hell are they and where to find them? Well, projects are a type of direct practice. I talk about it in great detail in this video right here. But basically, the best way to advance in anything is to practice in the context which is as close to real applications as possible. For example, to learn computational neuroscience, you should not limit yourself to watching video lectures or reading textbooks. The highest priority should go to attempts to solve real problems under your own steam, such as writing scripts to detect and analyze spikes in the voltage signal, or building a simple integrated fire models to play around with them. Undoubtedly, coming up with meaningful project ideas can be tough. By far, the best way is to join a research lab, which also has a ton of additional benefits, such as continuous mentorship and the potential to publish in journals. But when you are just starting on your own, here is one potential suggestion. As you are reading research papers, always look for some aspects of data analysis or modeling which excite you. If there is something that resonates with you, you can set up a mini project for yourself to first make sense of the author's code, which is usually available on something like GitHub, and then create a simplified version of it on your own. For instance, if this is a paper which contains a computational model of a network of neurons which develops rhythmic behavior, check out their code, what modules the authors are using, what is the big picture of their approach. Then you can go ahead and try to create a smaller model by using a similar methods to see if it generates some rhythmic behavior. It's not ideal, but it gives you the way to practice on real problems that are currently being solved by research groups. When you are choosing or coming up with a project, I think it's important to follow two simple rules. First of all, make sure that it's something that's dear to your heart. If somebody recommends you a topic, but it doesn't bring any sparks of excitement, then it's probably best to keep on searching for something else. This helps to make sure you are fully invested into following the project's path until its completion. This is especially relevant when there are no external motivators for you to pursue it. Another thing to keep in mind is the Goldilocks rule. The work, first of all, shouldn't be too difficult for your current level, or otherwise you will get discouraged. But at the same time, it should not be too easy, because it has the risk of feeling too boring and pointless. The sweet spot is right at the edge of your abilities. Hard enough for you to feel the sense of accomplishment when you complete some intermediate milestones, but at the same time not too hard to make sure you don't abandon it because you don't make any progress. What's so great about these tiny independent research projects is that you don't merely follow some toy examples from textbooks, but learn firsthand how to deal with real data. Now, if you're not a part of a lab, it may be unclear where to get such data in the first place. Luckily, nowadays there is a number of datasets which are openly available online. You can use specialized resources such as openneuro.org or neuromorpho.org. As an alternative, you can always email the authors of the particular paper you like to ask them to share some portions of their data. And don't feel shy to do it, it's a totally normal practice. If I were to leave you with one thought, it's this. Don't just passively sit and learn about computational neuroscience. Dive right in and attempt to actually do some meaningful computational neuroscience. Remember that without direct practice, it's impossible to advance. And the sooner you start, the better. Go get your hands dirty. Go spend hours figuring out how to do something on your own, resisting the temptation to just look at the solution or copy and paste someone's code. Remember that it's much better to come up with a clumsy, inefficient script that's written on your own than to read tens of books or papers on the similar topic. That's all I have for you today. And from the bottom of my heart, I really wish you the best of luck on this quest. If you have any questions that I haven't addressed in this video, leave them in the comment section down below. If you liked the video, share it with your friends, subscribe to the channel if you haven't already, and press the like button. Stay tuned for more interesting stuff coming up. Goodbye, and thank you for the interest in the brain.